us, right?
Yes.
Okay, so welcome to my presentation. It's a systematization of knowledge on the security of ASCON modes. We already saw two presentations on permutation-based hashing. This is a different one, and it covers authenticated encryption. So it's about authenticated encryption. And the core idea of authenticated encryption is that we have a key, associated data, a plain text, and a nonce. And the plain text gets encrypted to the ciphertext, and the tag authenticates the nonce, the associated data, and the plain text. And together with this associated data, there is a function called authenticated encryption, the inverse, that gets us input a key, a nonce, associated data, ciphertext, and tag. And it returns the plain text if the tag is correct and nothing otherwise. And in the last decade or so, there was a lot of attention on authenticated encryption. It started a bit earlier, but mostly in 2014, the CSAR competition started. And the CSAR competition was a competition for the design of some authenticated encryption schemes. Basically, a portfolio of authenticated encryption schemes. And roughly 5 years, this competition ran. There were like 57 submissions. And actually, roughly 10 out of them were sponge-based or duplex-based. And eventually, ASCON was selected as one of the winners in the portfolio, namely in the category lightweight. And soon after, NIST started the lightweight crypto competition. So from 2019 till 2023, they focused on lightweight authenticated encryption and optionally also hashing. They also got 57 submissions. So I think that's mostly coincidence, but there is some overlap. But there were more sponge and duplex-based schemes because the sponge and the duplex is really useful for lightweight authenticated encryption. And eventually, last year, 2 years ago, ASCON was selected as overall winner. And let's just try to see how ASCON looks like. So these are the designers of ASCON. So that's Schafer, Mendel, De Browning, and Eigelzeder. Some of them are actually here, so you can ask them for a signature. So authenticated encryption is actually the same in both variants, roughly, more or less. It's a duplex-based scheme. It's a duplex sponge or sponge trap inspired, but with some twists. So there are key blindings. I will show you later. There's also the hashing included in the lightweight crypto competition scheme, which was not in the CSAR competition. And that's just a sponge-based hashing and zoffing. I will give you the high-level idea of the ASCON mode. And ASCON is based on sponge wrap. So sponge wrap uses a permutation. In ASCON is 320 bits. ASCON actually uses a permutation on the outside, an outer permutation P, and an inner permutation Q, which is roughly a round-reduced variant, both on B bits, 320 bits. The state is split into an inner part of C bits and an outer part of R bits. C is the capacity, the security parameter, and R is the rate. Most notable difference is that you do key blinding. So you have a key as input to the permutation, and after the first permutation call, you do an extra key blinding. And also at the end, you do key blindings around the permutation. So what happens, we have the state, we initialize the state with a key and a nonce. We permute, we add the key to the bottom part, and then we're just going to absorb the associated data block by block. You do the main separation, and then you just absorb the plain text, squeeze the ciphertext as much as you need. In the end, you do one more key blinding, you permute one more key blinding again, and then you get your tag. And because the mode, the ASCON mode, resembles ideas of sponge wrap, it makes sense to actually check what's the security of sponge wrap, what do we have, and can we rely on this? And sponge wrap was introduced in 2011. In the introduction of the duplex, Bertoni et al. Introduced sponge trap as authenticated encryption scheme. And they proved that security followed from the indifferentiability of the sponge. So because the sponge is indifferentiable, you can get security of sponge trap. In 2015, me, René Nittenbach, and Visage, we improved this result. We looked at the full state duplex, and we get a better bound for sponge trap. This was significantly improved in the generalized duplex by Dame, me, and Van Asch in 2017. It's a very complex construction, complex proof, but it gave a much better bound on the duplex, which implies better security for sponge trap. Later, De Browning and me looked at the leakage resilience of the scheme. So in certain settings, this duplex even achieves leakage resilience. And 2 years ago, I wrote a guide, a duplex guide that kind of summarizes the main results and explains how they actually turn to sponge wrap, or basically monkey sponge wrap. And this gets very close to Ascon, but not quite, because Ascon has key blinding, so it doesn't fit. There was one more scheme in 2014, Jovanovic, Leux, and me. We proved NORCs, and we also claimed security on Ascon. We said, well, it carries over to Ascon, but without a proof. And the bottom line is that these results do not apply because of these key blindings. The key blindings generically actually get better security. So this was the reason for researchers to look at Ascon specifically and derive dedicated proofs. And the first main one is by Chakraborty et al. In 2023, they proved single user security in the non-suspecting setting. And the non-suspecting setting is that the attacker has to take a new nonce every time for encryption, and the attacker is actually kind, so it behaves like this. Roughly independently, but a bit later, Lefebvre and me, we proved multi-user security of the Ascon mode, both in the non-suspecting setting and in the nonce-misuse setting. And in the nonce-misuse setting, the attacker is naughty and it may repeat nonces. Soon after, Chakraborty et al. Extended their analysis also to multi-user security in the nonce-misuse setting. But actually, analysis of Ascon dates back a bit more. So in 2019, Guo et al., they looked at leakage resilience of permutation-based schemes, and they claimed multi-user security nonce-misuse resilience, which is somewhere between nonce-misuse resistance and nonce-respecting. They also derived security under leakage resilience. And in 2024, we looked at an even stronger version of leakage resilience called state recovery, where the attacker may even learn part of the state of the Ascon node. However, this looks quite a solid analysis of the Ascon node, but this turns out to be not true. So first of all, these two results were only proof sketches. As actually mentioned in the paper as a proof sketch, but also should permit a flaw. So we figured out that there is a flaw. We described the attack in this work, but I will not talk about this. So if you look at it like this, well, it's not a very satisfying situation. And that's what this systematization of knowledge is about. So we clean this up, and we do a dedicated analysis of the Ascon mode in various attack settings. So in general, we give a complete overview of the generic security of the Ascon authenticated encryption mode. We look at 6 security models, so 3 flavors of conventional security, nonce-respecting security, where the attacker always uses a new nonce for encryption, but possibly for decryption, it can repeat nonces. Nonce-misuse resistance, where the attacker is really bad and it may reuse nonces. And nonce-misuse resilience, which means that the attacker may reuse nonces. We don't care about this, but evaluations for new nonces should be secure. Then we look at 3 flavors of leaky security. We look at bounded leakage resilience in leveled implementation, where we assume that the outer permutations are strong enough, but the inner ones may be weak. We look at security under state recovery, where the bad guy can even learn part of the state, the inner state, and we hope to still achieve some level of security. And we look at security under release of unverified plaintext. And for all of those, we categorize existing results and we drive new results if there is a gap in the results in the state of the art. And yeah, we derive all new bounds and matching attacks. And all results hold under the assumption that the permutations are identical. Well, the result is huge. We have many different proofs. I will just give you the to the attacker for what we do. And we look at confidentiality and authenticity. And this is, in fact, the only result where we can rely on the existing state of the art. So we managed to rely on the work of Chakraborty et al. Those bounds carry over. We do give matching attacks. And what we see is, well, I didn't bring my pointer, but so the bounds are roughly similar. The main difference is this QD over 2 to the tau to the T for authenticity. Security holds as long as these terms are less than 1. one of the mu keys. Just a key recovery attack. It's exhausting key recovery attacks. The third term is a collision between a construction query, a state in a construction query, and a permutation guess. And the third one is where the attacker, the fourth one, n over 2 to the c, is where the attacker actually makes a permutation call offline that hits a certain targeted inner part. And this term, actually, this QD over 2 to the t up to n over 2 to the c, appears in all the bounds. And we call this the core term. So this is the term that always appears in all the bounds. And so this was nonce respecting security. Then we look at nonce misuse resistance. For nonce misuse resistance, we point out the flaw in the proof of Chakraborty et al. We take the result from Lefebvre and me 2024, but then in the setting where the two permutations are identical. And we get a bound which is slightly worse for authenticity. So first of all, confidentiality is broken. You can not get confidentiality if the attacker can reuse nonces. But authenticity holds with a bit of a loss because the attacker may learn out the part, so you get mu times m. Nonces, but we still want to get security for fresh nonces. And we get comparable bounds. I will not talk too much about the bounds. It's not so interesting for now. But you see that nonce misuse resilience is somewhere between nonce respecting and nonce misuse resistance. And this is actually true. I mean, there is an implication from right to left. So the leftmost is the most restrictive, the rightmost is the least restrictive, and the middle is somewhere in the middle. And this is what we derived for the classical conventional security notions. And then we go for leakage resilience. For leakage resilience, we have 3 layers to the bottom. In leakage resilience, we also assume the non-resilient setting as a nonce misuse resilience. So we give up on repeated nonces, but we hope to get security if the nonce is unique. And we look at 3 settings of leakage resilience. One where there is no leakage. It sounds a bit silly, but just for making the picture. One where the leakage is limited to, say, 1 bit or 1 byte or the Hamming weight of 1 byte, something weird. And one where the leakage is actually unlimited, where the attacker may, for instance, get the whole state. So first of all, leakage resilience, no leakage, it's just equivalent by nonce misuse resilience to nonce misuse resilience. This is by definition of the model. The attacker may learn in a leakage of the permutation call the entire state. The bound degrades. Most notably, we get birthday bound in C, so n squared over 2 to the c. That's basically corresponding to hash function security, because if the attacker learns the state anyway, you more or less have hash function security. And leakage resilience limited, if in limited leakage, well, it's implied. The other way, it's conditionally implied. It really depends on the leakage model that you take, but this is very subtle. It really depends if you, I mean, if you want to do analysis for specific leakage functions, it is actually subtle. So we just took the bound by implication. And finally, we look at state recovery security. And state recovery security is where the attacker, well, the outer permutations are secure, but the inner permutations may be weak, and the attacker may learn the state. Then confidentiality is void, but authenticity holds. And we already proved this in 2024, but now we reproved it in the setting where the permutations are the same. And finally, we have a release of unverified plaintext security. And a release of unverified plaintext security, decryption may release the plaintext before the verification is done. And that's, well, it's not a clever way of implementing, but it could happen in certain settings. And actually, release of unverified plaintext security, the authenticity portion is implied by state recovery security. But we even get a slightly better bound. Yes, and roughly is also at the same line of this limited leakage, because release of unverified plaintext is some kind of limited leakage. So this is what we roughly did for ASCON. Just to give you some numbers, this means, for instance, for a nonce respecting security, we get security as long as the offline complexity, so the time complexity of the attacker, is at most the minimum of 2 to the k divided by mu, 2 to the b divided by the online complexity m, and 2 to the c. and mu is the number of users. So as long as the offline complexity is at most this value, and for authenticity, we additionally have the number of tag forgery attempts is the most 2 to the t, we get security. If you then go to nonce misuse resilience, well, we get a birthday in 2 to the c roughly, so m times n for 2 to the c, so the bound degrades a bit. Nonce misuse resistance, confidentiality is empty, security and authenticity still holds. And then if you go to state recovery, it gets even a bit worse, but you still get some level of authenticity. And if you then look at the concrete parameter choices of the ASCON AED parameters, so the red one, ASCON 128A, that's the NIST standard, the upcoming NIST standard. It takes a 128-bit key. B is 320, C is 192, R and T 128, 128. Then we get security as long as N is at most 2 to the 128 divided by mu, where mu is the number of users. So the attacks, there are various attacks in this authenticity setting. It's really interesting to look. And the ASCON hash and ASCON soft, that's just sponging. It's just exactly the sponge hash function, but then with variable length squeezing. So we saw this in the previous slide. So we have a permutation P on 320 bits, B bits 320. C is the capacity, R the rate, so B plus C, B is C plus R. And it outputs new bits. New is 256 for ASCON hash, but it could be unlimited for the softs. And because it is a sponge, we can rely on the existing results. And in 2008, Bartoni et al. Proved that the sponge is indifferentiable from random as long as n squared is at most 2 to the c. So up to the birthday bound in the capacity. This implies security for the classical settings, so like collision resistance, second pre-image resistance, pre-image resistance. Basically, because if someone wants to, well, the collision resistance of the hash of the sponge is at most the distance from the sponge to the random oracle plus the collision resistance of the random oracle. So we can compose these bounds. The best attack was actually worse. And Lefebvre and me in 2000, Charlotte already mentioned it before, we had a tight bound improved pre-image resistance of the sponge, which also applies to ASCON hash. And if you then plug these into the parameters of ASCON hash, ASCON soft, and ASCON Z-soft, which is a customized soft, we basically get collision resistance as long as n is 2 to the 128, pre-image resistance, second pre-image resistance as long as n is 2 to the 128, and pre-image resistance not up to 128, but even 192. As a bonus, there's also ASCON PRF, but it's not in the standard, as far as I know. But it is in the papers. But let's just go to the conclusions. So there's much more in the paper. Actually, all the security models, the relations between the models, the meaning, the reason why we chose certain models, all discussions is in the paper. Also discussions on how we bound multi-collisions, discussions on why we take different permutations or not. All proofs and attacks, of course, they are in the paper. What we didn't cover is, for instance, related key security. We did cover multi-key security, which is similar. We didn't cover related key security. And also we didn't cover security if the keys are not random, but distributed according to some distribution. This was done in the duplex proofs, for instance. We did not cover security under fault attacks. We did cover security under sidechain, under linkage resilience, but there are results on fault attacks. One thing we also didn't cover is the variant with nonce masking. So in the NIST standard, they also suggest masking the nonce with extra key material to use.
So any questions?
Hi. I just have small question that I didn't really understand why there is no gap in the limited and unlimited leakage resilience proofs.
Yes, there should be a gap. The problem is that in the unlimited, it just leaks the state. Yeah, but it's related to state recovery. For limited, the attacker can actually, well, we assume the attacker can choose the leakage function, like this number of bits of the state, depending on the input. So it can kind of maybe tweak the input to get, well, it's artificial. It's really an artificial attack, but the attacker can say this leakage function on the permutation leaks the first bit if the plain text is this, the second bit if the plain text is this, and then you have conditional equivalence. So this arrow the other way, it's conditional. But if you look at specific leakage functions, so last year with a PhD, with a bachelor student, actually, we looked at security of SUCs under Hamming weight leakage. And then you get a much better bound. So then this condition doesn't hold and you can get better security, but that's actually very hard to analyze. Okay?
Thanks.
Okay, thanks. I think we don't have enough time, so let's thank Spark again.